The first example that we have today is a spring, and so that kind of goes along with what we've been talking about. Probably the easiest way to picture the effect that we're going to try to deal with this first problem is to imagine a slinky. Have you all ever had a slinky as a toy? Okay, so if you imagine a slinky, you know, those of you who don't know what it is, it's basically a really soft spring such that the spring constant of the spring is very low relative to the mass of the spring. And what you can do is if you stretch it out a little bit, you can actually cause there to be waves through that spring. Sometimes it's called spring surge, or you can actually watch a wave pass through the spring. The reason this is important is that if you have a spring that is driven at a frequency that matches sort of a natural frequency that that spring has, the surge effect can get very large, and it can end up causing the spring to fail before you would otherwise have expected it to. And so we care about the frequency that springs are driven so that we can avoid this effect of spring surge, or at least keep it to the point where it's a minimal effect. Okay? And so here's an example where we can come up with maybe how fast we can drive a spring safely before it starts getting into this kind of an effect. You know, what frequency can we drive it at? All right, for this exact problem, it says that we are applying a sinusoidal displacement, so a time-dependent displacement to the spring. Okay, the spring has 14 total coils and is composed of 26 gauge music wire. In case you're curious about that music wire, you can look up the properties for the music wire in table A28, which is in the back of the book. A28 says that a music wire with a 26 gauge has a wire diameter of 0.063 inches. Okay, and that would be that wire diameter D. Okay, so I'll just save us a little bit of time looking that up, but you can find it in table A28. Okay, what we need to do is make a conservative estimate for the maximum safe frequency that we can drive this spring. We're going to do that in hertz rather than in something like radians per second. And we're going to find that maximum safe frequency that we can drive this spring. Other thing that we know is that we're going to say the mean coil diameter for this spring is 3/4 of an inch, and that it has squared and ground ends. Okay, so where we look for this topic is we're going to look to page 527. There is an equation there that we are planning on using. So it's equation 1025. Okay, and that equation says that the frequency, okay, and generally when you see the letter F, although I've actually seen some examples in some textbooks where they don't follow this, but usually when you see a letter lowercase f, that means that they're expecting you to be using hertz for the unit. In other words, a whole cycle per second rather than radians per second. Generally, if you want it to be in radians per second, you'll usually see the variable omega. Okay, so but we have f. This is going to be equal to 1/2 of the square root of the spring constant k times the gravitational acceleration g, all this divided by the weight of the spring. Okay, and actually what this really gives you, this gives you what they call the first harmonic or first fundamental frequency of the spring. Truth is that a spring has distributed mass and distributed elasticity, and so it can have, any spring can have multiple resonant frequencies that it might exhibit. What we are actually concerned about, though, is the resonant frequency that is the lowest, all right, because that's the one that we are most likely to start infringing upon with the frequency that we drive the spring, all right? So that's why we're going to kind of ignore the other frequencies and just focus in on the first fundamental frequency here. All right. So the other thing that it tells you, though, is that this is an equation that makes sense, but you can find the weight of the spring based on a fairly simple calculation that's basically just kind of a volume times a density, if you want to kind of boil it out to its base. But here's how that works. That weight is going to be equal to pi squared times d squared times the mean coil diameter d. Okay, so pi squared times wire diameter squared times mean coil diameter times the number of active coils. Okay, and that's I should mention this. We're concerned about the weight of the portion of the spring that is active. Okay, so that's why we're using n sub a as opposed to n sub t for this equation. Okay, and then this gets multiplied by, in this book, they a lot of times call this the unit weight. It's also sometimes called the specific weight, but it's like density, but it gives you weight per unit volume as opposed to mass per unit volume. Okay, and then all of this divided by 4. Okay, and that is equation 1027. Okay, and so what we're going to do is find this first fundamental frequency based on these two expressions right here. So F is going to be equal to 1/2 of the square root. Okay, how do I find my spring constant? Okay, I don't actually have that spring constant boiled out just yet. So I tell you what, before I start filling in this frequency equation, let me actually do a little bit of a sidebar over here. How do I figure out K? Okay, same equation we've been using for last couple of lectures. It's equation 10(9). Equation 10(9) says d to the 4th g over 8d cubed n. Okay, where the one in the denominator is the coil diameter, and the one in the numerator is the wire diameter. This is equation 10(9). Okay, so I already mentioned that the wire diameter that we have here is 0.063 inches. Right? Where do we get an elastic modulus, or this is actually the modulus of rigidity, excuse me, modulus of rigidity G? Okay, yeah, I believe it's table 10.5. Okay, we are dealing with music wire, and for music wire with a diameter of 0.063, such as this one, we look that up, and it's basically the second entry under music wire in that table. For that wire diameter, it gives you 11.85 MPSI. Okay, so 11.85, and that actually is times 10 to the 6th PSI. Okay. In the denominator, I put in 8. And then the mean coil diameter is given over here of 0.75 inches. That's cubed. And then finally, my number of active coils. How do I get my number of active coils? Okay, I have 14 total coils given in the problem. And according to table 10.1, which is back a few pages, if you have squared and ground ends and 14 total coils, you subtract 2 to get the number of active coils. Okay, so we put in 14 minus 2 for my number of active coils. All right. So when I punch in these values, which again I'll skip that, I'm sure you guys have the ability to compute this. It ends up giving me 4.609 pounds per inch. Okay, and that's my K value. And so what I do is I take that K value and I put it up here, 4.609 pounds per inch. All right, now what's G? Okay, G, we're working in the US system here, and so probably the most familiar expression of gravitational acceleration for the US system is 32.2. And what are the units on that? Feet per second squared, right? All right, now what about the weight? Okay, well, I'll tell you what, I'll keep going with my sidebar over here so that I can fill in the weight. Okay, this is just going to be equal to pi squared times your d squared, which was 0.063 inches, times the mean coil diameter of 0.75 inches, times my number of active coils. Again, that's just 14 minus 2. Now, what about my unit weight for this spring? Okay, there is a table. It's actually in the same table as you find elastic constants, elastic information for most materials. Music wire is, basically a steel, and so we're just going to look under here under carbon steel and get 0.282 pounds per cubic inch. This is table A5. Okay. Okay, and then all of that gets divided by 4. So when we punch all of this in, it ends up giving us 0.02485. pounds. Okay, so we put that down here. All right, so now let's take a look at these units real quick and make sure that we're on the right track. Okay, what happens with pounds? Okay, pounds cancels pounds, but now I have a per inch and then I have feet. All right, so what should I do with that? Okay, probably want to do 12 inches per foot, like this, and that gets rid of the inches and the feet. And what am I left with? Yeah, so I have 1/2 squared is what's in under the radical, and I take the square root of 1/2 squared. That just gives me 1/2, and that gives me, this gets a little tricky because we always say radians is unitless, right? Well, the tricky part is cycles are also unitless, right? So you actually have to read the context of the problem. And if you're curious about that, you can actually look in this same section in the book. There's an unnumbered equation before the one that I'm using here where it tells you where they got this from. And that original equation had a factor of pi in it that goes away whenever we go to converting this into hertz, basically. That's why the equation that we're using comes out in hertz rather than in radians. Okay, so figured I'd mention that. But what this ultimately means is that we've handled our units the way that we need to, and it ends up giving us a frequency here of 133.85 hertz. Okay? So that's our first fundamental frequency. So my next question is, do we want to drive it at that frequency? That's probably our last thing we want to do, is drive it at that frequency, right? So, you know, it's not enough to say, don't drive at this frequency. We need to know a frequency range within which we are okay to drive it, all right? And so what I want to do is draw your attention to the following page, page 528 if you're in the 10th edition. And it says the fundamental frequency, the fundamental critical frequency should be greater than 15 to 20 times the frequency of the force or motion of the spring in order to avoid resonance with the harmonics. All right? That's a little guideline that's right in the text of the book, page 528. And so what is the most conservative thing for us to do? Okay? It says 15 to 20 times. Okay, in that range, 20 is the most conservative factor to apply here, and here's how you do it. So this is, you know, maybe a frequency allowable. All right, it's just going to be equal to 133.85 hertz divided by 20 as the most conservative estimate. All right, and that ends up giving you 6.69 hertz. Okay, and basically we're saying that by driving it a good bit slower than that first fundamental frequency, then it's unlikely that we are going to induce any kind of a destructive resonance into the spring. All right. So any questions on this problem? The question is, why is it 15 to 20 times? So basically, the idea here is that, or at least this is how I take it, you could actually end up having standing waves in the spring that might, they might end up having sort of a lower frequency in effect than what we just computed the fundamental frequency here. I can't tell you more than that. It's just, I guess by testing, they've decided that this is a pretty good guideline to use to make sure that you're outside of that range. Now, one thing to ask real quick is 6.69 hertz, is that a lot? Okay, so you're basically saying, let's just say it's 7. You're cycling a spring 7 times a second, all right? And this is for a spring that actually has a fairly small diameter. The wire diameter is only 0.063. So that means that it's not a super stiff spring, right? And so, it actually makes sense to me, I guess, is what I'm saying, is that, this doesn't seem like an out-of-bounds presumption, okay? Again, the idea is if you got all the way up to 133.85, that would be the worst, right? That'd be you intentionally driving it at that fundamental frequency. So we're going to back off of that significantly to make sure that we don't accidentally hit any harmonics that might cause problems. Yes, sir?
So the initial F is in units of like 1/2 second. Is the 133 what that equation equals, or did you have to multiply by something?
I did not have to multiply anything. If you take those numbers and plug them in, it gives you 133.85. That number, based on the text that surrounds it right there at that point in the spring, or in the text, that number is coming out in hertz if you actually read around that equation. And the reason why is that the previous equation they got it from, they actually canceled a factor of pi that was in that earlier expression. All right, any other questions? All right.